Hi there. My name is Tarun, and last summer I did a project on the experimental proof and practical application of Leroy J. Krzyzewski's algebraic formula for rocket nozzle throat diameters. I've always been extremely passionate about rocketry, gradually learning about rocket design through books and the internet, but I've encountered bottlenecks in my learning where mathematical complexity keeps me from progressing further. Rocketry and the math that permits it are complicated. However, there are often mathematically simpler approximations for calculating variables when the most accurate answer isn't necessary. These approximations can be used for smaller and simpler systems, or more importantly, when the subject needs to be explained or learned in a simpler format. The average rocket nozzle works by first compressing exhaust through the throat, speeding it up in the process. However, if the throat is too small, then the flow is choked and thrust is lost. Then the nozzle expands to match the exhaust pressure to the ambient pressure to accelerate the exhaust as fast as possible. The nozzle, therefore, is fundamental to the rocket engine, effectively being the system to transfer power from the engine to force out of the back. The formula used was included in the book called How to Design, Build, and Test Small Liquid-Fueled Rocket Engines. This was converted to an online format on an early website, providing me an avenue to learn about engine design while I advanced into higher mathematics. My first project with this resource was a cost-effective experimental proof of its accuracy and a detailed explanation of how to apply the method to a full nozzle design. I used a combination of this formula and NASA's formula for expansion ratios to design a small-scale rocket nozzle. This augmented the accuracy of the method while still staying true to maintaining a mathematically simpler method. Then, I designed and built a compressed air thruster using recycled materials to form a cost-effective test platform. The pressure-exposed components were all rated up to at least 200 psi, with only other components on the test stand being made from commonly available hardware. The thrust test stand consisted of the thruster, mounted on a free-rolling platform, with a scale mounted on a backing wall, refreshing readings every second. The resulting thrust was compared to the results of NASA's thrust force formula to find out if the thrust is within a reasonable percent error of its scale. In conclusion, the project did successfully validate the method, with a reasonable error of about 4%, of which most could be attributed to external variables out of my control and scale of manufacturing.